Hi, I'm Jay, one useful friend upon your wish. This is my first production of the YouTube video in English in my Hofstad Professor channel that started 2 weeks ago. I'm planning to produce YouTube videos in English or Korean for this channel. Please encourage a beginning YouTuber newbie by clicking on like and subscribe. From the thumbnail of this video, you might have expected that this video is about the chi-square test, but in fact, this video is more about regression, especially the log linear regression, than about the chi-square test. My goal is to set up some theoretical background on which to guide you to this powerful statistics technique, the log linear regression, from the discussion of the chi-square test. Now let's begin with the chi-square test. In statistical analysis, it is often more important to ask when we use the particular test than to ask what the particular test is. We ask first when you use the chi-square test. The world is full of data. We see numerous data in the form of frequency tables or what we call contingency tables. A contingency table takes the form of cross-tabulation in terms of two or more categorical variables. Let me give you a classical example from Gravita-Wallau's famous statistics textbook, where we find the relationship between sex and color blindness. This is a frequency table observed from 1000 cases, and these cases are cross-classified by two categorical variables, variable X, which is sex, and variable Y, which is color vision. As you can guess from the table, researchers have hypothesized that color blindness tends to occur differently between males and females. Then we have this question: do sex and color vision interact? Or does gender affect color blindness? To answer this question, we use the chi-square test. Here's the general procedure to run the chi-square test. First, we start from the observed frequency table, which we call FO, and then we mathematically produce or calculate the expected frequency table, which we call FE, based on the totals of each column and row of the observed frequency table. Let's look at the example. This is the same observed frequency table in the previous slide, but this table also shows you the total numbers of each column and row in the margins of the table, and these total numbers are called marginal frequencies simply because they appear on the margins of the table, and in fact, from these marginal numbers, we mathematically calculate expected frequency values like this. Expected frequency values are the numbers we expect to obtain simply by chance or by logic. For instance, if we toss a coin 50 times, we expect to see 25 heads and 25 tails simply by logic or by chance. Here, 25 heads and 25 tails are expected frequency values that will occur by chance or by logic. Anyway, let me show you how these expected frequency values are calculated from the observed frequency table based on the marginal frequency values. This is a mathematical formula to calculate the expected frequency value from the observed frequency table. According to this formula, the expected frequency of each cell is calculated by first multiplying the row frequency by the column frequency, and the product is divided by the grand total. This way, if we want to calculate the expected frequency value of the male and red-green color blindness cell, you first multiply the marginal frequency of male, which is 400, by the column frequency of red-green color blindness, which is 80, and then the whole product is divided by the grand total of 1000, and then the final calculation will be 30, which is the expected frequency value in the corresponding cell of the expected frequency table. This way, we obtain all the values for the expected frequency table, and then we calculate the chi-square value using the difference between observed frequency and expected frequency values using the formula here. And finally, we obtain the p-value of the chi-square calculation here from the assumed population chi-square distribution with a particular degree of freedom, and then decide whether or not we reject the null hypothesis that there is no interaction between x and y variables. So the logic is quite straightforward, but we face this puzzle. Why is the null hypothesis of the chi-square test stated differently from the null hypothesis of the t-test or ANOVA? As you know, the null hypothesis, or simply H0 of the independent samples t-test, is stated such that the population mean of sample A is the same as the population mean of sample B. Likewise, the null hypothesis of one-way ANOVA is stated such that the population means of 3, 4, 5 or more than 5 samples are the same. On the other hand, the null hypothesis of the chi-square test is stated such that there is no interaction between x and y variables of the contingency table. Strange and wacky, isn't it? To this puzzle, many people think that they know the answer based on quite a circular logic, which goes as follows. The chi-square test with two categorical variables is called the chi-square test for independence, and for this reason, the null hypothesis of the chi-square test claims no interaction between the two categorical x and y variables. Well, do you see the circularity in logic here? It is circular because you can always say reversely, the null hypothesis of the chi-square test claims no interaction between the two categorical x and y variables, and this is why we call the test the chi-square test for independence. So we still have to find out some constructive non-circular wisdom. Here's the key to the puzzle: regression. First of all, remember that the fundamental logic of regression lies on the almost all statistical tests. The t-test and ANOVA are actually specialized forms of regression, and the conventional null hypothesis of the t-test and ANOVA can be stated in terms of regression equations. This is a very important theoretical topic, but I can't discuss this topic any further, so for the topic of t-test and ANOVA as regression, you can reserve my future video by clicking on like and subscribe. Anyway, following the same logic, the chi-square test is a special form of regression, especially the log linear regression, and the conventional strange null hypothesis fits into the logic of model building in the log linear regression. In log linear regression, we build log linear models, that is, regression equations, where the natural log of each frequency value is predicted from the linear combination of the categorical predictors in the cross tabulation, or simply the frequency table. Now, the fundamental idea is that these observed frequency values are in fact the predicted outputs of a saturated model. On the left-hand side of the equation, we have the natural log of each frequency value, and then on the right-hand side of the model, we first have lambda, which is the constant effect, and then lambda x, which is the main effect of x, and then lambda y, which is the main effect of y, and finally lambda xy, which is the interaction effect of x and y. This is the saturated model. What about the expected frequency table then? We have so far memorized the well-known formula where we multiply the row frequency by the column frequency and then divide the product by the grand total. Let's replace this common classroom instruction with the idea of log linear regression. Now we set up a restricted model here. This model comes from the saturated model after removing the interaction term, which is lambda xy, from the saturated model. So on the left-hand side of the equation, we have the natural log of each frequency value, and then on the right-hand side of the model, we first have lambda, which is the constant effect, and then lambda x, which is the main effect of x, and then lambda y, which is the main effect of y, period. Now, to predict these expected frequency values from the restricted model, we have to calculate or estimate each parameter of the restricted model, that is lambda, lambda x, and lambda y. The estimation of parameters in the log linear model is a very complicated mathematical process, which I don't want to cover in this video. Interested audience, my friends, please leave comments and let me know that you are interested. We know that the chi-square test compares the observed frequency values with the expected frequency values. We have also learned that the observed frequency values are predicted from the saturated model, whereas the expected frequency values are predicted from the restricted model. Therefore, we can say that the chi-square test compares the restricted model with a saturated model. Then how do we compare the two models? Here's the logic. First, we want to explain FO, observed frequency, with as few parameters as possible. Second, observed frequency values are predicted from the saturated model. And third, if possible, we want to predict observed frequency values with a model without the interaction term lambda xy. Hence, we build the restricted model like this. And fourth, in log linear regression, the chi-square test tests the null hypothesis that the restricted model predicts the same values as the saturated model. Therefore, 5, if we obtain a p-value greater than 0.05, we fail to reject the null hypothesis and we conclude that we don't need the interaction term lambda xy in the saturated model, since the restricted model without the interaction term predicts the same values as the saturated model. 6. On the other hand, if we obtain a p-value smaller than 0.05, we reject the null hypothesis and we conclude that the interaction term lambda xy is necessary in the regression model, since the restricted model cannot predict correct observed frequencies. Here's the summary. If p is smaller than 0.05, then reject h0 and conclude that we need the interaction term lambda xy in the regression. On the other hand, if p is the same as or greater than 0.05, then accept, i.e. fail to reject h0, and conclude that the restricted model without the interaction term lambda xy predicts the observed frequencies, so there is no interaction between x and y. Now the puzzle is solved. We now understand why the h0 of the chi-square test is formulated strangely, such that there is no interaction between x and y variables. After all, the null hypothesis of the chi-square test in terms of log linear regression is restated such that the restricted model predicts the same frequency values as the saturated model. So what's next? Now that you understand all this logic, you are ready to learn the powerful technique of log linear regression in the upcoming video. Upcoming videos will present you with not only theoretical backgrounds of this advanced technique in a lucid way, but also necessary R codes to run the log linear regression on a multi-way frequency table like this. I have taught log linear regression quite a long time. This is the poster of SLE 2010, which was held at University of Copenhagen, Denmark 13 years ago. In that summer school, I taught 1-week course titled Log Linear Regression in Corpus Linguistics, and I was applauded by a lot of audience who said, "Wow, this is a really powerful technique. It will be very useful." So this time, I'm here with you, friends. I wish I could be one useful friend upon your wish in this YouTube channel. Please click on like and subscribe. Thank you. See you next time.